Hi everybody, this is Dominic Forbush of Sandia National Laboratories, here to talk with you about how to model cable and tether type connections within WEC-Sim. This is a really common user inquiry, and it's because cables and tethers represent a really cost-effective way to couple floating bodies together or to couple floating bodies to the seabed. And even though it's simple and cost-effective, it can be numerically complex in that those cables only support a coupling force when they're in tension, and they tend to deliver a lot of coupling forces in tension, but they don't transmit forces in compression. That's easy enough to state in terms of an equation, but to actually implement numerically and within the blocks that WEC-Sim provides can be a bit trickier. Hopefully after today you'll know how to do it. There are two different major approaches that you can take in WEC-Sim to model this cable, the cable block and the multi-body linkage. We'll talk about both of these in this presentation, but we'll start with the cable block. This is the example that you find in the WEC-Sim applications repository of the same name, and you can also find documentation on the cable block feature in our user manual's advanced features section. The WEC-Sim cable block is a block like any other found in the WEC-Sim library that offers a one-size-fits-most solution that directly implements this equation within your WEC-Sim model. You define the properties of this cable block from the WEC-Sim input file or the Simulink interface, just like any other block you might find. And this block is intended to couple bodies together, but you could use it as a mooring if you wanted to. Now, it's worth noting that all we're trying to get correct here is the force transmitted between the bodies via the cable. We're not actually trying to resolve the kinematics of the cable motion itself. And to this end, the constraints on the motion at the point of connection between the cables and the body is defined by an interspersed WEC-Sim constraint block, shown there by these arrows, that are defining how the cable connection point is free to move relative to the connected body. Here we are looking inside of the cable block itself. You'll note that at its core, it's a MATLAB function call that is a direct implementation of the equation at the bottom of the screen. The reason it's in a MATLAB function is if you were to want to use a different cable force equation or perhaps a more complicated model, you could just get in there and modify this function and you'd be good to go. The arguments that you have available by default are entering from the right. They are cable stiffness, cable damping, cable equilibrium length, and the cable's initial length. The latter two arguments can be calculated in a variety of ways that we'll get to in a moment. These calculations are then applied to the position and velocity of the extension of the cable, which is assumed to act at the center of the cable length by this translational PTO actuator. You'll note also that there are two drag bodies that are assumed coincident with the ends of the cable, and these can be used to apply a viscous damping force acting on the connected bodies that results from the interaction of the cable motion in the fluid itself. Again, we're not actually trying to resolve the kinematics of this motion. We just want to have some tunable parameters here so that we can account for it with respect to the connected bodies. On this slide, we see two code excerpts, the top of which from the WEC-Sim input file where the cable class has been declared, and the bottom of which is a look inside of that MATLAB function block that we were zoomed in on the previous slide. Starting with the WEC-Sim input file, we see that the user has to define not only the parameters within the cable class, but also they need to initialize the location of the constraints describing the motion of the cable endpoints. These constraints in the model are indicated by their color code, yellow and green, and the cable parameters that are utilized by the cable force calculation MATLAB function are shown by their own color code. The last parameters here, highlighted in orange, are related to the quadratic drag that's exerted on the drag bodies that also lives within the cable block. In the first code block, the WEC-Sim input file, notice that the cable pretension argument is actually commented out here. Now there are ways that we can use this as an input argument, and we'll get to that in a subsequent slide. But note that it also doesn't appear as an input argument to the MATLAB function block in the lower code segment. And that's because the pretension will be used with a different set of input arguments to calculate the initial length of the cable. So even though it doesn't appear in here as though it affects the calculation, in fact it does. The second thing that we'd like to note is that the third index of the velocity and position in the MATLAB function is what's utilized to calculate cable tension force. That's because this third index is the index that aligns with the axes of extension in the translational actuator PTO block inside the cable block. Within the Simulink multibody solver, no matter what orientation the cable is at, that translational PTO will always measure its extension along that third index of position and velocity. Here we're looking at the same WEC-Sim input file code excerpt, specifically the cable length and pretension arguments. And we're looking at how different combinations of declaring the cable length or pretension affects the calculation method of cable length from within the cable class implementation. The first possibility is that the user has not declared either a cable length or a pretension. In this case, the first method is used. The pretension is assumed to be 0, and the cable length is simply calculated based upon the positions of the constraints to which the cable is connected. In the second possibility, the user has defined a pretension but not a cable length. In this scenario, the constraint locations are used again, along with the cable stiffness property to back out what the equilibrium length of the cable must be. In contrast to this, if the user specifies a cable length but not a pretension, the pretension will be calculated from the difference between the specified constraint location and the equilibrium cable length. Now finally, if you specify both of them, because the cable end positions are fixed based upon their connected constraints, we've actually overdefined the system here, and this will result in a compilation error. So if you successfully run a WEC-Sim model that includes a cable block, it will produce an output structure that includes the extension, the rate of extension, and the tensile force along the cable. The only thing to note here is remember that the force is always applied along the line of action of the cable, which is described by the relative position of the constraints or the PTOs at its endpoints. Here the pros and cons of the cable block method are summarized. On the pro side, this is a one-block solution that offers a quick and easy way to model cable connections, and it will work for a lot of WEC-Sim simulations. Additionally, the tuning parameters offered by the drag body blocks allow you to closely approximate physical reality with even this simple implementation. On a similar note, although the previous example we were using constraints to define the cable end connection points, we can equivalently use PTOs, which will allow us to apply additionally a damping or a stiffness force between the motion of the cable end and the connected body. On the cons side, very fundamental to this implementation is a logic check in which the cable equilibrium length is compared against the cable's current length. Now, any logic check in a numerical simulation, time-stepping numerical simulation at least, is going to result in a pretty stiff system to solve. If you already have a lot of numerically stiff elements, perhaps you're using a PTO or PTO sim blocks, this can actually make your model run intractably slowly or perhaps not run at all. And particularly in that scenario, we would encourage you to try the other cable modeling method within WEC-Sim that we'll discuss in the subsequent slide. The other method that we would encourage for modeling cable type linkages in WEC-Sim we're referring to as the multi-body linkage. And this is a workaround that's encouraged for highly stiff systems where the cable block is just not going to work. And basically what we do here is through a system of rotational or spherical PTOs, we create a linkage that just by virtue of its geometry can support a load only in tension. And so we're sidestepping the need to do an explicit logic check and just letting the amalgamation of PTOs and bodies used to model the linkage to implicitly handle this for us. Here we're looking at the pros and cons of this modeling method. First among the pros is we can model an inextensible cable in this way. We don't have to intersperse a translational type PTO element within this assemblage of PTOs and bodies if we don't want to. And if we choose not to do so, the cable will act perfectly inextensively. This contrasts with the cable block implementation because in the cable block, you must explicitly define a cable stiffness and damping. Secondly, as we mentioned, there's no explicit logic check here in these equations, which can make it more suitable for solutions that have a lot of other numerically stiff elements within them. And finally, additionally, we have a lot of tuning flexibility here. We can tune at the bodies, we can tune their drag parameters. At the interspersed PTOs, we can tune their stiffness and damping. And while we're not getting to the point where we're actually resolving cable kinematics, this effectively looks like a very low order lump capacitance model of the cable, and we can use it to tune its response. Thinking about the downsides of this modeling method, we require a minimum of 3 PTOs and 2 bodies to resolve just the motion of one cable. In the event that you don't have a numerically stiff system already, this is likely to be quite a bit slower than just using the single block cable model. Secondly, if cable slack events or shock loads related to emerging from a slack event are a key concern for you, because the output structure of this methodology will be splitting the cable dynamics across all of its constituent PTO and body blocks, cable slack events are not as easy to spot in post-processing, although they are readily apparent once you know what you're looking for. And the third con is something we'll discuss in more detail on the next slide that I'm referring to for now as a snap-through instability. The snap-through instability refers to the instability that happens in this approximation of a cable when the solver is trying to figure out what's happening at that central node when the cable is just barely in tension or just barely not. Now, this is a non-physical dynamic. We're approximating the cable motion with the presence of this central node. But when the cable lives in this transitional state, the solver can waste a lot of time and effort trying to resolve this oscillatory motion of this central node, even though it's not actually significant to the coupling forces between the bodies that we actually care about resolving. In very extreme cases, this can cause the simulation to bog down and not solve in a tractable period of time, or to fail entirely. This can be mitigated to some extent by tuning the stiffness, damping, and quadratic drag of the connected bodies and PTOs, and that's the recommended workflow if you have to use the multi-body linkage method and you're encountering the snap-through instability. This has been Dominic Forbush with Sandia National Labs. I thank you for listening to this training on the cable implementation within WEC-Sim. I highly encourage you to check out the attached link there where we have all of our additional webinars available, and our documentation for all of the advanced features and basic features as well can also be found through that link. Thank you for your time today.